We're going to move on to our next session. We'll be looking into the next generation of aviation propulsion. The leader and moderator of this will be Rich Wahls. Rich, take it away. It's all yours.
Thank you. Yeah. Testing. There we go. Okay. All right. Thank you. I'm very happy and honored to be here moderating this session on next generation aviation propulsion at the John Glenn Symposium with a very distinguished panel. We have some industry and government representation here. For those of you who don't know me, my name is Rich Wahls. I've been with NASA for over 30 years, and I'm currently in the Aeronautics Research Mission Directorate as the Sustainable Flight National Partnership Integration Manager as of about a month ago, I guess, now. The way we're going to run this session, we're going to have about 25 minutes or so of kind of opening remarks from our panel. Then we'll have some discussion, and towards the end we'll take some questions from the audience. I'm going to introduce the four panelists first, and then so I don't have to interrupt the flow as we go through. We're not going to go in the order that we're sitting. So I'll introduce the panelists in the order that we're sitting. Our first panelist will be Brad Belcher from Rolls-Royce Liberty Works. Brad has been in the business over 40 years and has focused on experimental tests, advanced technology development, management of advanced programs for civil and military applications, and he's now the program director and customer executive for their work with NASA and the FAA. Following Brad will be Christine Andrews from GE Aviation. Christine is the executive leader in charge of hybrid electric systems. Is responsible for programmatic systems and design for all hybrid electric systems. She's been at GE for 9 years and has held various leadership positions across many disciplines within aviation engineering. Jean Thomassin from Pratt & Whitney, Canada, is the executive director in charge of new product and service introduction. He looks at what's coming next, he says, so beyond the next generation on technology and business models, and he also runs their turboprop hybrid electric propulsion demonstrator. And finally, Barb Esker from NASA. Barb recently has a new job in addition to doing a previous job, but Barb is the Assistant Deputy Associate Administrator for Missions in our Office of the Associate Administrator for Aeronautics. While she's doing that, she's still currently acting as Director for the Advanced Air Vehicles Program, where she's responsible for overall planning, management, and oversight of all the ARMD efforts to develop innovative concepts, technologies, and capabilities that enable revolutionary advances for a wide range of air vehicles. So a very nice, distinguished cross-section of folks here. I'm going to turn it over to Brad for some opening remarks.
Okay, thank you, Rich. If we could go to the first chart for the Rolls-Royce. And Rolls-Royce, we are pioneers of power. If I can borrow the clicker. There we go. Thank you. Let's see if I can advance this. We are talking about an electrifying future and an exciting future. The electrification is both a literal and figurative term here because we will be talking a lot about electrification, but also a lot of the other elements of advancing our propulsion capabilities in a more sustainable way. So our pathway at Rolls-Royce towards zero carbon and the decarbonization of our power and energy projects. You'll see the three pillars shown here. Step changes in efficiency of gas turbine engines. Gas turbines themselves are still extremely efficient. The question is how we power those engines. So we are making the engines more efficient and in their integration with the airframes while we're doing the second pillar of pursuing sustainable aviation fuels. We are doing a lot of leading work in characterizing and validating many of the sustainable fuels, both blends as well as fully synthetic sustainable fuels. The photograph in the picture, I'll talk more about that aircraft in a following slide. That is our Rolls-Royce 747 flying test bed out in Tucson, Arizona. And prior to the COP26 conference you've heard referenced in this seminar that was held in Glasgow back in I believe November, we were able to fly with a 100% SAF, fully synthetic blend. And then the third pillar is developing third generation technologies, which you see a demonstration of an electric aircraft, but also we are pursuing a number of alternative fuels such as hydrogen. And I'll mention that. So electrification is not new to Rolls-Royce. You'll see in these images terrestrial, marine, submarine even, and then other power systems that Rolls-Royce works on, including nuclear power, which is a potential source for much of the power we need for sustainable fuel generation for our future aircraft. Our progress in 2021 to deliver towards our net zero goals, in the upper left-hand corner you see our fuel cells that were highlighted at the COP26 conference for emissions-free power generation. That's one of the ways we are working on power for the future. Going to the right, you'll see the Axel aircraft. We're very proud of that effort. That was a 100% electric-powered air speed record holder. We were able to smash the speed records late this last year and set a closed course record of 345 miles an hour in an all-electric aircraft. This was not just for the fun of it. We learned a great deal about integration and working not just with the batteries, the power electronics, and the integration into the airframe with that effort. Lower left, Rolls-Royce is launching small modular reactors in the nuclear power business. We are using our expertise from over 60 years working with the Royal Navy with mobile compact reactors and looking to be able to provide these systems for clean power transition. The final photograph, we carried out the series of tests. I can tell you that today we are doing a pre-flight brief. I am managing an FAA clean contract where we are collaborating with Boeing and the FAA to fly an enhanced nacelle technology, a short inlet nacelle that will reduce weight and drag for fuel burn reduction. And that aircraft has already started its flight campaign, and I'm hoping that we will be back in the air tomorrow to continue that program. So a couple of things, I didn't put a chart out, but I've been very carefully watching the news this week as we've been here at the seminar because there have been a number of announcements coming out of Farnborough that are very relevant. We are announcing our progress towards our new UltraFan demonstrator, which is a very large, very efficient engine that will also serve as a test bed for a number of technologies that we can incorporate across our product line. And then there was a press release that former NASA Aeronautics Administrator Jaewon Shin is with Hyundai now, and there was a photograph of him with our Rolls-Royce chief executive announcing that Rolls-Royce is partnering with Hyundai to provide the power for the advanced air mobility platforms that they are working on. Also, we have made some announcements about hydrogen testing. We are currently partnered with NASA to do outdoor testing at their Stennis Center and are in discussions to plan out doing future hydrogen engine testing at that facility. So I'll leave it at that. So thank you.
Sure. Thank you very much. So similar to what Brad went through, we have a lot of things going on at GE. It's a very exciting time. We have 3 committed demonstrators, first of which is a hybrid electric demonstrator in partnership with NASA on the Electrified Powertrain Flight Development Program. This will take our hybrid electric components and actually fly them. We have a very good partner in Boeing to do the aircraft modifications and actually get us into flight. I think we're working with the right branch of Boeing that's leaning into this in the aircraft modifications with Aurora Flight Sciences. and bringing in the expertise that Boeing has coming out of Seattle and their experience on the 787. It's a really exciting program, and this truly is the time that we're taking hybrid electric concepts from the ground through altitude testing and finally into flight. And it will change the future of aviation as it opens up a new landscape in how we design jet engines and reduce aircraft emissions. We have a hydrogen demonstrator committed with Airbus. This will fly middle of the decade. This will also be an in-flight demonstrator. We've been working on our hydrogen program for well over a decade in conjunction with our power business. And we're really excited to see this one get into flight and get some of the answers to many of the questions that come along with burning hydrogen. And finally, we have the CFM RISE demonstrator. This is a commitment to 20% fuel reduction over current product, which is the LEAP, released in 2016. It's a huge step change. The feature that's most notable is the open fan technology that provides a lot of propulsion efficiency. And then second, the one near and dear to my heart is the electrification and the hybrid electric that you see via the lightning bolt and the two streams there. But I will say the core technology also is major advancements through the compressor, turbine, advanced materials, as well as a combustor. Eventually, the RISE program will also include burning hydrogen. It's planned day one to be SAF capable, as all of our engines are today. As Brad mentioned, a lot of announcements coming out of Farnborough. I'm particularly proud of the announcement on the left-hand side. In conjunction with NASA at the facility just outside of Sandusky, the Plumbrook Station, we have done altitude testing of our entire hybrid system. So we've advanced from component testing to the system and taken that up to 45,000 feet and proven that this system can indeed operate, so we're ready for flight test. This is a world first and what really sets the bar for electrification in the aircraft industry. Very big accomplishment, excellent partnership with NASA. NASA and GE worked hand in hand to not only stand up the facility, but also complete this test campaign that has us set up for success on all future electrification campaigns. And on the right-hand side is a public commitment that we made with Airbus via CFM to go fly the RISE engine. This will happen in the second half of this decade, but that takes that ground test that we announced last year and says we're going to go put it in the air and show that it indeed does deliver its promises of fuel burn reduction. And it's a huge announcement as we really gear up for the next generation of products. So very big air show for us. Couldn't be any more excited about both pieces here, especially on the hybrid front, both a huge testing milestone as well as getting this closer and closer to product with the RISE announcement. And just to get a little bit deeper in hybrid electric technology, it kind of stole the thunder with yesterday's announcement at Farnborough with our successful test campaign. But the hybrid electric campaign is going to be a megawatt power class, multi-kilovolt class. That's what we've already done in our test campaign at NASA. We tested it up to 45,000 feet. And this is much more challenging than what we see the initial product offerings being. If we can go do this, and I think that we've already proven that we can be a test rig, then the future hybrid electric configurations are going to be far less challenging, and we're ready to start incorporating that into the RISE program. It was a huge feat and something that we're all very proud of at GE.
Hi, good morning. So I'm from Pratt & Whitney. So our approach to sustainability goes beyond just electrification, right? We have to look at it globally. So the first perspective is to improve the thermal efficiency of the engine. We've been doing that. I have an example in the coming slide, our latest product. We also, obviously, the engines today, they are compatible with SAFs. I mean, if you have the source of fuel, you can use up to 50% blend, and all of our next platform will be 100% SAF compatible. We are doing demonstrators as well. We believe in electrification. Electrification, in a sense, it is linked to the first line item. So you have got to use the electrical power to help the cycle in the end. And we're looking as well as at hydrogen. We don't think that the long pole of the tent is to burn hydrogen. We've been burning it. The challenge is into using the energy that you put into the fuel to keep it cold, because it's very likely that we will have to carry liquid hydrogen on board. So you want to use that energy as a sink into the cycle. So we're looking at these advanced cycles around with hydrogen. Thank you. So we talked about propulsive efficiency. So we've introduced a product in 2016 that is a big improvement into propulsive efficiency. So what it is we introduced a fan drive gear system in series with the fan. So it opens up the design space. So you can change. We can play with the size and speeds of the low spool versus high spool, and it leads to significant improvements in CO2 and emissions reductions, as well as noise. So we're proud of it. It's a solid platform going forward to the future. We just launched the GTF Advantage that improves the fuel efficiency and also improve the thrust and the thrust capability of the engine. So it's a solid platform. Again, we talked about improvements in the propulsive efficiency, so we've done it. About demonstrators, so this has been launched last year. This is my main focus at Pratt. So it's a turboprop demonstrator program. It's targeting 30% mission fuel burn efficiency improvement. It was launched in 2021. We've selected most of the suppliers. Many challenges along the way. It's very important that we make that demonstrator to the right scale. So it's a 2 megawatt power plant on a 35,000-pound max takeoff weight airplane. It adds to the challenge, and we understand better the safety elements that are related to the flying the airplane. So the hardware is on the way. We've been running the electrical motor. So we talked about Farnborough, Collins. So we're Pratt & Whitney, but we're working with our sister company, Collins, within Raytheon. We announced the 1 megawatt motor that's actually going to be on that airplane was announced this week in Farnborough as well. And the other thing that we're looking at is, I spoke about improving the efficiency of the vehicle, reducing the fuel consumption, but there's also new capabilities that the electrification may bring. So we also announced a smaller scale hybrid electric demonstrator this week, where we will try to understand what can be enabled downstream for runway independence and things like that. So that's very interesting. It was announced as well in Farnborough. So that is the Pratt & Whitney story around sustainability. Thank you.
Good morning. So as Rich said, I'm Barb Esker, and I'll be speaking on behalf of the Advanced Air Vehicles Program and the NASA Aeronautics Research Mission Directorate. I'm going to take a little bit different approach to my remarks this morning. I'd like to start at this 60,000-foot perspective and recognize that electrified aircraft propulsion means a lot of different things to a lot of different people. The challenges, the solutions, the technologies are all different depending on the size, class, and the application in mind. But what these technologies all have in common is that we're developing design tools. We're growing the knowledge base, which ultimately is going to put more tools in the toolbox for the designer going forward. Starting on the left-hand side, for very small UAS or drone vehicles, these vehicles fly primarily battery-based, all-electric propulsion systems. They're pretty well understood, and industry is working very effectively at pushing the design technology forward in this class. The next category are these small passenger-carrying vehicles represented there by an eVTOL and by the NASA X-57 Maxwell vehicle. Many of these are battery-based, but not all of them. We're pushing the envelope not only on the technology, but I think more importantly in this arena, what's needed is open and verifiable data. This data is absolutely critical so that the certifiers, the folks that are setting the standards, can set those standards efficiently and effectively for this emerging industry. The data that we are pulling together and we're working on within our agency is going to be largely open, that can be shared with folks like the FAA or ASTM or SAE standard setting bodies. And this is important so that this industry can get off on a good foot and build a reputation of being safe and reliable. And then as you get to the next size class, in the regional jets or the single aisle systems, the challenges are different still. In this case, we're not anticipating purely battery-based systems, but as you heard from my fellow panelists, we're looking at hybrid or turboelectric systems. These are systems where you can take advantage of the best attributes of the electrical power system, but also the best attributes of the Brayton cycle-based gas turbine. Now, when you look at these systems, the challenges not only reside on the electrical and the electrical components or in the gas turbine, but there's also very significant challenges associated with how those two systems work together. How do they interact? How are they going to interface? How are they controlled in an integrated fashion? And then what does that integration mean for the broader integration between the propulsion system and the airframe itself? So I'd like to focus just a little bit on the Advanced Air Mobility Mission, or Urban Air Mobility Mission, as many folks refer to the key use case. In this case, we're working on two different fronts. As I mentioned, we have the X-57 Maxwell vehicle, which is under development. It's slated to go to first flight, I think, late this summer or early in the fall. That was an opportunity to engage our NASA workforce in a very high energy, high impactful way in developing that vehicle and bringing it to flight. In addition to that, I want to mention the eVTOL activity, which is highlighted here. This is an area where these vehicles are going to have very high cyclic use. They're going to be used very rapidly for short hops, largely, and perhaps from city center out to the airports and back, which means that the propulsion systems are going to experience stressors that are a little bit different. So the question is how can we design these systems for the ultimate reliability that's going to be necessary, again, for safe and efficient operation. So highlighting some work here in Cleveland at Glenn Research Center, we've recently developed and brought operational a reconfigurable electric lab. That electric propulsion laboratory has the capability for up to 200 kilowatt source and single and multi-string configuration options. It's an opportunity to test a variety of electrical configurations, including the ability for fault insertion. As I mentioned, the data derived from these efforts will inform the technical standards committees and the test procedures using those standards. Now, we don't just take the data and toss it over the fence to the certifiers, but we have our NASA subject matter experts actually working shoulder to shoulder with the folks in these SAE and ASTM committees as an example. This allows those persons that are setting the standards to understand some of the nuances and the significance of the data. In addition, we have regular meetings at the senior leader level to ensure that that information, that coordination happens at the very top levels of the agencies. And I'd like to transition now to the larger transports, the regional jets or single aisle aircraft in particular. What you're seeing here is lovingly known as the swoosh chart. It depicts the set of activities that comprise the Sustainable Flight National Partnership, for which Rich Wahls is the newly selected Michigan Integration Manager. As you can see, there's a lot of activities, and we're tackling all aspects of the aircraft, including the airframe configuration, the ability to produce composite aircraft at high rate, as well as the propulsion systems highlighted here. As mentioned, these are going to be largely hybrid electric or turboelectric based systems as far as from our perspective. And I think you've heard some of that from my fellow panelists. You're looking at power levels that are upwards of 1 to 2 megawatt in these propulsion systems. And we're going to be tackling it on multiple fronts. So first off, we're going to be advancing the next generation electrical components towards higher power densities and higher efficiencies. And this is an area where we have partnerships with industry, as Christine mentioned, for example. And we work closely with them on not only what's on the horizon, the immediate horizon, but what's next on that further further off horizon. You've heard mention of the NASA electrical aircraft test bed, or the NEAT facility that's out at our Armstrong Test Facility out in Plum Out there, we have recently completed a test with the Navy. This was a demonstration of a fast, lightweight, altitude-ready solid-state circuit breaker for hybrid electric propulsion. That team recently completed a technology readiness level 4 test, and we'll be going to a technology readiness level 6 test next year at altitude. Second, we continue to work with our industry partners through the Electrified Propulsion Flight Demonstration Project. Christine alluded to that. That's an opportunity to take these technologies into flight. Christine talked about the GE effort to put an integrated power system on a Saab 340, but we also have an effort under that project with the MagniX company out of Washington. They're looking to fly a de Havilland Canada-7 aircraft with an electric power system powered by 2 PT6 engines and 2 MagniX Magni 650 electric propulsion units. These efforts are both in ground testing and flight testing, as I mentioned, and those efforts don't happen in isolation with each other. There's got to be a feedback loop, bringing together what you learn in flight back to what you can exercise and test on the ground, and vice versa. And then thirdly, we have to pay attention to the interface between the gas turbine and the electrical sides of the propulsion system. These two systems have to be able to work seamlessly together. So to that end, we've been working towards power extraction levels on the order of 10 to 20% from that gas turbine. We recently completed some testing of fault management and energy management techniques that will be important for this interface. We've tested a control scheme on as to how and when to pull power off the engine spools, that's off the low spool and the high spool, without disturbing the engine performance and operability. To wrap up from where I sit, this is a tremendously exciting time. I think use of the word electrified is key. It's electrifying future in more ways than one. But most importantly, these systems hold true potential for really revolutionizing the aviation system looking forward, and to make it dramatically cleaner than what it is today. I don't think any of them are a panacea or a slam dunk, but it's going to take concerted effort because the potential is truly, truly there.
All right, thank you. I want to start off following on to what Barb was just showing. There's a wide range of markets here, from small electric vehicle, local area kind of vehicles, all the way up to the vision of transports that mostly affects climate and carbon. How do each of you see the relationship between the demos you're doing and the applications to the smaller vehicle markets versus the larger vehicle markets? Do they relate? Do learnings translate?
Sure, yeah, I'll go ahead and start it. For GE, the EPFD program is the ultimate engineering test bed. We chose the power class and the voltage class to take what we see in the foreseeable future hardest type of system into flight, such that we're ready for futuristic concepts like a distributed propulsion system. But if we ease back down on the power and voltage levels, we're ready to go into the narrow body market with the RISE program. Similarly, we can adjust, tune, and tweak those power and voltage levels for all markets. And it really comes down to, and Barb did a nice job of walking through this, electrification can be used in many different ways for the different market segments. And it's going to come down to the configuration that provides the most benefit. And what we're doing on EPFD is proving out, I would say, the baseline level of what Barb was talking about between what spool when in our demonstrator, and from there we'll be able to incorporate that into the most efficient way possible, regardless of the market segment. So it's applicable to all market segments. The configuration may look a little bit different. The underlying physics really remain the same, and it opens up a whole new way to design for each one of these. And once you've got the physics down, you can really optimize for any specific platform.
But you see, like, system architectures are kind of transferable. You're not making decisions
absolutely.
that, okay.
Yeah.
Brad?
And to just continue on, the power electronics, a lot of the connections, the integration within the airframes, a lot of that. I think I'm on. Can you hear me? Thank you. Is this one working? There we go. Thank you. So a lot of the components, as Christine would say, are building blocks. They're transferable, and depending on the size of the aircraft you're working on. Rolls-Royce, we are developing and have already demonstrated sub-megawatt and megawatt class applications. When you look at the limiting power requirements for an aircraft, often it's takeoff power. Then once you get to cruise, you don't need as much power. So this is where you get the benefit from distributed propulsion, electrical, and even potentially mechanically distributed propulsion. So those are ways in which you use the propulsion where and when you need it, and then you stow it or reserve that. So yeah, I agree with what Christine has said and what Barb had outlined. We are working on many of those systems and are involved with flying. I agree that the larger wide bodies are a bit off in the future. Batteries, the power density of batteries is somewhat limiting now to the smaller class, but we think that to get the additional range, speed, and lifting capacity, the hybrid electric systems are going to be very useful in that mid-size range.
If I may add, maybe just to put some numbers in perspective, in our turboprop demonstrator, we're using a 1 megawatt roughly electrical motor to boost the engine, and that's about 50% of the total power. So, but the same 1 megawatt motor can be used on a distributed system on a larger airplane, and it represents something like less than 5% of the total power. So that's sort of like, the same technology brick can be used in different markets, but the architecture of the fundamental system may change. But the fundamental physics is constant. Yeah, I agree to that.
Yeah, and Rich, I think I'd like to take a little bit different tact to answer your question and focus on the people. One of the things that we're seeing is that the learnings of the people that are doing the work, is broadly applicable. So we found opportunities to bring our workforce in on smaller systems, battery-based systems, but that sparks an energy and an insight that then ports over and can be applied to the larger systems and the larger technology challenges there. So I think that this is an opportunity to grow the workforce out there and the capabilities that they bring to the table. The other thing that involves people is this idea of getting the right information into the hands of the regulators and the standard setters. We're doing that on the smaller all-battery systems, for example, in the X-57, but that same dynamic will have to exist in the larger systems. How do we bring the right data, that will help govern the standards for the larger aircraft systems? And that's a function of the people that are engaged.
All right, I'm going to go off on the track of people here. What's really exciting is all the demonstrations we're talking about, and they're not just component, they're system level integrations. Do you have trouble finding people to staff them? What kind of challenges do you have in doing so many demonstrations at the same time? And what would you do?
Be bold and say yes. It's a field, and I'm assuming that all my colleagues will agree, including NASA as well. There's just not people with this experience. This is a new frontier, and we are learning as we're going. It's actually been excellent to partner with NASA, because in our reviews, it's the first time we've talked to somebody else that has experience, maybe not all the time 100% relevant, but brings a different thought to the table, and we can compare experiences and have a discussion that's not just based on our own, testing and experience. So that's been absolutely fantastic. I actually liked following the keynote speaker earlier today. I'll put a plug in, getting more people, first of all, in engineering, second of all, interested in these types of growing areas. I mean, I'm specifically, and I think the rest of the panelists are most interested in hybrid electric, but also the other technologies, including burning hydrogen. There's a whole world out there, and we truly are at this inflection point as an entire industry, and I'm very happy to be on a panel with my industry peers that are all pursuing this sustainability initiative. And so whatever we can do to get more people interested in wanting to join the movement, I'm happy to sign up, because it is a very niche thing, and to the point made by the keynote speaker, if people don't know this is a career field, I don't know how else to get them interested.
So as we move down the line, I'm going to add to the question. You know, we're here at a university. In aerospace or in engineering in general, where should we enhance the programs? What skills are you missing?
Yeah, to go a step further, aerospace is already a diverse area where you need a lot of very specific skill sets, and then some people rise to a systems level. But down at a more fundamental level, we need this unicorn that is somebody who has both aerospace and electrical combined together at a fundamental level. So that is something where we work with universities. Rolls-Royce has a long history of our university technology center partnerships. So we work with universities in the U.S. NASA has just issued their solicitation for their University Leadership Initiative that is currently on the street, and we are engaged with our U.S. university partners to pursue that. So you're absolutely right. STEM education up into the higher levels is key, and letting our university partners know the challenges and the kinds of skill sets that we need is very crucial.
Some more crosstalk between departments.
Yes.
Yes. Barb.
So I agree with what's been said so far. I will add another little swizzle to it. I think that we need the expertise in distinct areas, be that aerospace engineering, electrical engineering. Those are absolutely key, and you need folks that are very interested and skilled at being, let's say, an inch wide and a mile deep. But we also need the systems folks. We need the folks that are dedicated to systems engineering, systems analysis, that are in contrast a mile wide and an inch deep, and because that's an absolutely important skill to bring to the table as well. And then that's not just enough. We need those two groups to work together, and when they need to work together effectively, because if that doesn't happen, these highly integrated systems are not going to come into being.
And I agree, and I would add, we've been working as well with trying to get to other industries, like the top end automotive. There's capacity there, and we've contracted a lot of work with partners around the world so that we could get the capacity because we committed to dates and we want to deliver the demonstrator. But on top of that, I would say in terms of skills of the future, and I don't want to be the boring here person here, but heat management. I mean, there's so many new systems. They all run at like 50 Celsius. It's very cold. So, whenever, if you work on electrical and other components, on chemistries, run your components as hot as you can. And but also, anyways, all that to say, heat management should not be forgotten here. It's an important element.
All right, I'm going to stay with you, Jean. Thinking about demonstrators, so I remember you were working on what was called Project 804 and then went on hiatus. How does that relate to what you're doing now, and more generally, in the process of doing these demonstrators that all of you are doing, what have you kind of learned along the way that if you were to start again, you might do differently, or?
Okay. Well, I mean,
what challenges have you faced?
Yeah. Okay.
Yeah.
So, I mean, it started as a corporate initiative. Again, between Pratt & Whitney and Collins, we have like the ingredients to make the system going. So 804 was the initiation of that. Yeah. But we engaged conversations with some customers, and we see potential, product and goal to there. So when we became Raytheon, at the same time, we kind of divested the Otis and Carrier. We became Raytheon, and all that to say that the project was repatriated up north because of the conversations we had with customers. So that's how it happened, right? And out of COVID, the government's invested, into COVID recovery's green initiative. So that sort of helped and fueled the system. In terms of big challenge, at the end, it's like we need to save fuel. It's like, we don't talk about that. We take it for granted because you electrify, you save fuel. But in aviation, an airplane designer told me once, he said, I look at three things when I design an airplane. He said, weight, and weight. So every pound that you carry needs to make its way into more efficient system. So anyways, the point is you need to save energy. So you want to do a mission from point A to point B. You want to carry so many people there fast. You got to do it with less energy than you used to do. Whatever fuel we use, whatever we do, whether it's SAF, 100% SAF, whatever the blend is, whatever the hydrogen is, it will be more expensive, right? So, anyways, that's the challenge to me.
How about any other kind of learning so far in the demonstrations?
A lot more blood, sweat, and tears than
Yeah.
anticipated. It's a humbling journey, and I'm positive we're not done being humbled. There's just so much to learn, but with that, and I'm sure the other panelists would agree, comes the greatest success.
Yeah.
You learn so much more through those hard times. And with our recent announcement, it feels like one of the crowns. And so you get this inflection point to look back and say, like, we've learned a lot through this that preps us for the next phase. But it's getting to the top of the mountain and not realizing how hard the climb was till you look back down and remember all of the lessons learned along the way.
To invoke a quote by former Secretary of Defense Donald Rumsfeld, we don't know what we don't know.
Yeah.
We in this industry have been on a journey of trying to evolve existing systems, existing turbo machinery, tube and wing aircraft architectures. So it has been an incremental journey as we try and eke out just ever smaller improvements. But we are on the precipice of doing some very radical things. And as Christine said, we're going to have to test. We're going to have to learn through experience. And we can predict what some of the challenges will be. We will discover some of those along the way. So it's going to be an exciting time for all of us and for the younger people coming into the industry.
Yeah, I think the folks that spoke were very, very eloquent. Appreciate that. One of the things I think we need to do, Rich, or do more of is to change how we define success. Because I think, as Christine said and as Brad said, success has to be measured by what we learn as well. Because some things are going to go right and some things aren't. And I would submit that when things don't go right is probably when you learn more, because you're not going to make those mistakes again.
Yeah, so I resonate with weight, and energy efficiency. And I think energy efficiency is never going to go away. Using less energy is going to benefit us no matter what. But you can't energy efficiency your way to net zero. So that's when we get into electrification and SAF and hydrogen and other fuels. If I put you in 2050, are we going to see a mix? Do you think SAF will ever? I mean, we're going to get there. Will it still be a key part of the world then? And along with that, could you speak to the infrastructure or terrestrial challenges that work into that, as to how possible those different energy futures could be?
Sure. Yeah, we've done a lot of work, and I've actually seen work similarly out of both Pratt and Rolls. And so I think we'll all have a very similar type of technology landscape here. By 2050, you're going to see more electrification, period. The fully electric, whether it be battery or fuel cell, is going to be still in that very small, low passenger, short type trips. I think you're going to continue to see a mix between gas power and electrical propulsion, whether it be fully distributed or a light distributed propulsion system with more advanced aircraft concepts, as Brad was mentioning. I think we'll bring those along on the journey. And then in terms of the fuels, I think Jean had a chart on this, on the entrance between SAF and hydrogen. SAF is always going to be, to me, the Band-Aid solution. When you can't do anything else, you can add SAF everywhere. Electrification is really the same. You can add it anywhere as well. But when you're going for that net zero, it's going to be very easy to add the SAF medicine. But it ultimately comes down to just burning less. So we need to continue to develop the core technologies, whether it's SAF or hydrogen. Hydrogen was going to take a little bit more time to develop. And as you mentioned, the infrastructure challenges with hydrogen in the handling, the distribution, the storage, the technician training in order to handle that safely is going to take a lot of time. SAF is much easier to drop in, but there also could be a divergence between what we do here in the United States and where Europe goes, and I think you're starting to see that with where they're spending their money versus where we are here in the U.S.
Do you think cleaning up of the electric grid falls in between SAF and hydrogen?
I do, and I think that's actually a shorter putt than certainly hydrogen. SAF has its own industrial challenges. It's not a slam dunk to start making that. So I actually think cleaning up the grid is actually the easiest, which helps our cause quite a bit.
I'll throw a little bit of a ringer in here, but there's a whole subject called the history of the future. So how many out here have seen the Jetsons? Sitting around on Saturday morning in your PJs with some cereal watching that fun cartoon show. The Jetsons got it wrong, just like almost every other prediction of the future, because when you look at the future through that lens, you're seeing everything as future. And that's not reality, because there are going to be legacy systems. So, I'll look at my watch for effect. We're at the mid or quarter century mark, and we're trying to be carbon neutral by the mid-century. The aircraft that we're building now are durable goods. They last 30 years. They will still be flying. So a big part of the fleet that's out there, we are going to do our best to come up with technologies in which we can retrofit. There will be some limited ability to do that. The biggest thing we can do with the legacy systems is to stop exporting carbon from below the surface and capture it above the surface and take advantage of what Bob referred to the Brayton cycle for efficiency with gas turbine engines. So I agree that's not the total solution, but it will be a big part of that solution as we learn better ways to electrify and to use alternative fuels. Hydrogen is wonderful. It doesn't have carbon in it, but creating the hydrogen for the aircraft takes energy. Distributing that takes energy. Hydrogen burns hotter, so you're going to now be making nitrous oxide instead of a lot of CO and CO2. So there are many challenges that a lot of sharp people in this generation and the next will be working on, but we are going to have to figure out how to transition from what we've got over that same period.
Thanks. While our last two panelists are addressing this question, if the audience is having questions, you can make your way to the microphone, and I'll try to take yours. But Barb and John.
So Rich, you asked about a vision for 2050. I think it will have to be a mix for all the reasons just cited. I don't think we can get to fully clean 100% vehicles across the board, as Brad said. These are capabilities. These are vehicles that are going to last 30 years when they come into the fleet. So we have to be able to acknowledge and address those. In this area, I don't think there's a silver bullet. In fact, I've heard it described as the need for silver buckshot, which means that there's got to be a lot of pieces to the solution that create that 2050 reality. For example, the grid has got to be cleaned up. I mean, there's carbon that's coming off of the grid that is what we're anticipating to be used to charge our batteries, right? So those are things that are way beyond the vehicle considerations, which is what we're all generally interested in here. But those are responsibilities that go over to our colleagues at the Department of Energy here in the United States, where they're looking at the cleanliness of the grid. And then producing hydrogen. Hydrogen's great. It's got some good attributes, but it's got to be made somehow. And right now, the process for making hydrogen is not a clean one by and large.
I would add that airplanes are very good. Airplanes flying all north of 100 passenger mile per gallon today, like the best in class 120. So I think we'll see airplanes in the 150-ish, right? And they will be through better cycles. So pressure, high temperature, high pressure will remain and will be there for a while. And that being said, I was on a COP26 panel 6 months ago, more or less, and that was the conclusion in the end. It was across transportation, across industries, rails, boats, trucks, and in the end, it's like, to your point, Barb, it's like there will be no silver bullet. We'll have to use all the technologies. You may burn hydrogen, you may use hydrogen in a fuel cell if the end user is electrical, but it will be a suite of technology that will be used in the future, hopefully in the aviation as well, if we can get the weight in the box.
Thanks.
Just got time for maybe one question.
Okay.
And then we'll move on. Does anybody have a question? If not, I do. Go ahead.
Yeah, good morning. My question is related to risk management. So there's a number of risks in the development of systems. You mentioned the thermal risk, the EMI with high power systems. Could you talk a little bit about what risks you all feel like, or in your opinion, the industry is going to take into flight tests versus what risks they feel like they need to buy down with ground testing? And are the ground testing facilities and capabilities currently, what is existing or needs to exist to support that?
Oh, I can take a shot at it. So, if you get down to the second level of details, like in the implementation, execution of the system. So the voltage, obviously, for the mass reasons, you want to increase the voltage of the system. So high voltage is a challenge, especially at altitude. So that's a big one. Arcing, EMI, like you mentioned. But there you could have like altitude facilities. You don't need much airflow to test the systems at high altitude, so it's not that expensive. So you could do a lot on the ground before you fly it. And then the battery thermal runaway is always, it keeps being a challenge. It will be a challenge. So we have to manage that as well. So I see those two big elements like in the nuts and bolts of what I'm doing now.
Any other comments?
Yeah, I think you cover actually the question. The person that asked the question covered a lot of the risks, but that's why we're following a very rigorous test campaign that builds on the building blocks. Such with the announcement we made at Farnborough, it was a very big deal to go from each component being tested at altitude and fully characterizing it to growing it into a system and testing it on the ground and non-altitude capability, and then taking that whole system and putting it, in the NASA NEAT facility and doing that at altitude up to 45,000 feet. And I would equate that journey to really the same way that we've been developing all engine component technology. While the landscape hasn't been developed such that it has been to date for a combustion rig with a single cup and a multiple cup and a full annular rig, we're developing that as an industry. And even if the three major players up here today haven't talked about it, I think you're going to start to see that standardization just come about naturally as we've identified, the risks and we develop what we would call internally at GE our design practice, or what the toll gate reviews and steps are to go do hybrid electric flight. But it's really no different, I don't see, from a risk management perspective than any other technology. And in fact, one of my biggest risks, and I'm sure the rest of the panel will smile, is supply chain right now.
Any additional comments on that question?
Well, the only thing I was going to point out is that going back to something Christine said earlier about being humble, I think we're going to learn things, in flight that we didn't anticipate today. So we have to be open to the possibility that there's going to be some things, in a risk sense, that we just simply can't anticipate until we try.
All right. I think with that, we'll close it off. I want to thank the panelists for being here with us instead of in Farnborough, but still watching the news so you could report to us. Thank you very much.
Excellent. Thank you very much. Yes, thank you indeed for being here instead of Farnborough, and be thankful that you're not in the heat over there, right? Record heat over there. So Brad and I were talking, it's nice to be in an air-conditioned conference room rather than out on the tarmac over there. Thank you very much to that panel. It was great. I'm a space, this is a space industry meeting, but it's always good to dip into the aero side of things. And it's really great to see how these worlds are really getting closer and closer together on the technology side of things.